Colligative properties. Have you ever made ice cream at home? And you have to put salt on the ice or it just doesn't work. Do you know why you add salt? It makes the temperature of the ice colder. It seems kind of weird, doesn't it? Isn't the ice cold? Well, ice is cold, but when you put salt on it, it gets colder. Ice melts at 0 degrees Celsius. If you put salt in it, it'll melt at about minus 10 degrees Celsius. That's significantly colder. That's a property called freezing point depression, and that's what's known as a colligative property. Colligative properties depend on the number of particles that are dissolved. They don't depend on the type of particle. So this is a kind of an odd set of properties because usually, properties depend on what kind of a substance you have dissolved. Colligative properties of electrolytes are going to be slightly different than non-electrolytes because electrolytes separate into multiple particles. So 1 mole of an electrolyte, like sodium chloride, is going to make 2 moles of particles. 1 mole of calcium chloride is going to make 3 moles of particles because it separates into calcium and 2 chloride ions. Whereas if you have something like sugar, which dissolves in water just fine, 1 mole of sugar makes 1 mole of particles. So what are these properties? One of them is vapor pressure lowering. We've talked about the concept of vapor pressure. We get a dynamic equilibrium between evaporation and condensation. We have a beaker with a watch glass over it to keep the gas from escaping. Well, when we put a solute into this solution, now the solute occupies some of those spaces near the surface and interferes with the evaporation of the liquid. If the rate of evaporation is lower, then when this comes to equilibrium, the pressure of that substance in the gas state will be lower. Lower vapor pressure because the solute molecules interfere with the evaporation of the solvent. Does that make sense? So that's kind of a simplistic explanation. It's relatively easy to understand, but that doesn't really explain this phenomenon. So here we have, looks like a cake plate, doesn't it? 2 beakers, 1 pure solvent and 1 a concentrated solution. So maybe this is water and this is salt water. If you leave this over a fair period of time, what will happen is that some of this solvent will move to the other beaker. Right? Like, what? If I could, hold a thought in my head long enough, I'd try this at home, but I always forget when I get home. This actually has to do with entropy, nature's tendency toward mixing. So here we have a pure solvent, here we have a concentrated solution. Nature's tendency towards mixing and spreading out energy is going to cause the solvent to move from one beaker to the other. And it's not magic or anything. Solvent evaporates from this beaker, solvent evaporates from that beaker. This is a closed system, and so solvent will condense into this beaker and condense into that beaker. And we'll see a rise in the level of liquid in the beaker that has the solute in it. Any questions? We can quantify this. Ralts Law is used to quantify vapor pressure. The vapor pressure of a solution is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. So if you have pure solvent, then the mole fraction would be 1 times its pure solvent vapor pressure, and pressure of the solution will be the same as. But if you have the more the less solvent you have, because you're essentially diluting it by adding solute, the lower the pressure of that solution will be. So the vapor pressure is directly proportional to the amount of solvent in the solution. Your book goes through this derivation. We can look at the vapor pressure lowering, delta P. We can derive it from this statement up here. Delta P is going to be the mole fraction of the solute times the vapor pressure of the pure solvent. So the more solute you have, the larger the change in the vapor pressure. Here's an example. And here we're talking about non-electrolyte solutes and non-volatile solutes. Because if it's volatile, that adds another layer. And then if it's an electrolyte, we have to consider the number of particles. So these are not electrolytes, just to keep things a little simpler. So calculate the vapor pressure at 25 of a solution containing 55.3 grams of ethylene glycol and 285.2 grams of water. The vapor pressure of pure water is 23.8 torr. So if we want to know what the vapor pressure of the solution is, we need to use Ralts Law. So the vapor pressure is going to equal the mole fraction of the solvent times the vapor pressure of the pure solvent. So we need to know the mole fraction and the vapor pressure of pure water. Well, the vapor pressure of pure water is given to us right here. We're given masses of ethylene glycol and water. Water here is going to be the solvent because there's a lot more of the water than there is of the ethylene glycol. Ethylene glycol is also a liquid at room temperature. So we need to take these two masses and convert them into moles and find the mole fraction. So we need the mole fraction of H2O, and that will equal the moles of H2O divided by the moles of H2O plus the moles of, we'll call it EG. So 285.2 grams of water